Good morning, Precalculus students. Today we're going to be talking about the dot product. The dot product can be used in the real world to help calculate the work that things have done. Hopefully you won't calculate how much work it took to put all this on the board. Anyway, so the dot product is a fancy way of saying we're going to multiply the like terms of two vectors like I times I and j times j and then add them together. It's written u dot v. So it's slightly different than multiplication in the fact that only like terms are multiplied together and then we're adding them at the end. So these dot products are generally going to follow the scalar rules of vectors with the addition that u dot u is equal to the magnitude of u squared. Okay? So when we're talking about vectors, parallel vectors, they'll have the same slope. They will be scalar multiples of each other. So for example, v is equal to ku when k is a real number. So basically, if you take both components and divide them, you should get the same answer for the I and j components. All right? Perpendicular vectors, we use the fancy word called orthogonal. So orthogonal vectors are perpendicular. This occurs when the dot product of two vectors is 0. The angle theta between two non-zero vectors can be found by using the dot product. So it's equal to the magnitude of u times the magnitude of v times the cosine of theta. And that's equal to the dot product. We can rewrite this as the cosine of theta is equal to the dot product of u and v over the magnitude of u times the magnitude of v. Whenever you're doing this, please be careful because the Schwarz inequality maintains that u dot v is less than or equal to the magnitude of u times the magnitude of v. So if you're working on these problems and your denominator is smaller than your numerator, you did something wrong. You'll need to go back and check yourself, okay? Furthermore, I just wanted to emphasize in case you hadn't picked up on it, I is the x direction and j is the y direction. That's how these unit vectors relate to the normal Cartesian coordinates. So now on to the tricky part of the lesson. You might have looked at this on your own and started freaking out. No worries. It's a little bit confusing. You have to read it a couple of times the way the book presents it. Basically, when we have a projection of u onto v, we're saying that's essentially how far the vector u goes in the direction of vector v. Okay? It's easier to think of this in terms of components than it is of projections. The component will be the magnitude or length of the projection. So remember, every vector can be considered the resultant of two or more vectors. So basically what we're saying is, well, if you take two vectors, you can always have the vector have a component of another vector. So it's really easy to use this to relate vectors to each other. Now, the magnitude of the projection is equal to the component. The projection will depend on the magnitude of both vectors and the angle between them. Furthermore, the component of u onto v will be u dot v over the magnitude of v, which is also equal to the magnitude of u times the cosine of theta. Similarly, the projection of u onto v is u dot v over the magnitude of v squared times the vector v. So projections, you'll end up with a vector in rectangular form, and components, you'll end up with a singular number. Okay, guys? Now, like I said, we take advantage of this in real-world math to do work. Work is force times distance, as you might remember from 9th grade. So when we're talking about force, we're actually only talking about the component of the force that goes in the direction that we're traveling. Okay? So this allows us to find the horizontal force exerted by a diagonal force. It's very useful for engineers. Anyway, I have several different problems on the board to show you examples of how to do things in the homework. So this first one is just the dot product. We have a vector u is equal to 3, 4, and v is equal to negative 5, 2. These are in component forms. Remember, the first one is a, the second one is b. We're going to multiply the like terms together, then we're going to add them. So we get negative 15 plus 8 is equal to negative 7. Whenever you do a dot product, you're always going to get a singular number. Okay, this next question finds the angle between u and v. We just use our formula. So just plug your numbers into the formula. We need to find u dot v, the magnitude of u, and the magnitude of v. We just went over how to find the dot product. You guys have been pros about finding magnitude, modulus, norm, whatever you want to call it. Easy peasy. We plug them all in, take the cosine inverse of that. Boom. You should notice something. This answer's in radians. Make sure that when you're finding the angle between vectors, unless it explicitly states that it wants degrees, you should be in radians. So, number 19, we're trying to find whether u and v are parallel, orthogonal, or neither. First, we're going to see if they're parallel. We take 2 divided by 3. That is unequal to 6 divided by -1. So there's not a real number k that when multiplied by v will give us u. Okay? So you just set up these ratios. If they're the same, they are parallel. If they're not parallel. We then do the dot product. If it equals 0, they're orthogonal. Our dot product equals 0, so they are orthogonal. 32, we're finding the projection of v onto u. This is the opposite of the formula that you saw on the board earlier. So when you're doing this, the smaller letter, the subscript, will be the one that appears in the denominator and on the outside. That should be u on the outside, not v, I believe. Anyway, we take our dot product, we find the magnitude, we square it, and then we plug our numbers in. Components even easier. We have less things to find, just the dot product and the magnitude. We plug them in. You should notice a projection will have rectangular form. A component will have one answer. That's because the projection, we're getting a new vector. The component, we're getting a singular number. So we take advantage of this for question number 53 in the book. You can read the description on page 680. It's a woman pushing a lawnmower at an angle of 60 degrees with the horizontal, and she's pushing with 30 pounds. We're trying to find the work that she does when she pushes at a distance of 75 feet. So we're going to need to find the component of the force that goes in our direction of travel. In other words, we're finding the horizontal direction of the force applied, because that will determine the amount of work she's actually doing. So we just take advantage of the second part of our component formula. Then the component of u onto v is equal to the magnitude of u times the cosine of theta. Our theta here is 60, our u is 30, and our d is 75. So we plug them in, we get 30 times the cosine of 60 degrees times 75. These problems are pretty easy in this section. Just make sure you don't get confused about the angle. I look forward to hearing your questions. I hope you guys have a wonderful weekend, and I hope you're enjoying vectors as much as I am.